Yeah.
Yes.
You're changing direction.
Because you're changing direction, yep. So velocity is speed and direction. And if you are changing velocity, then you're accelerating. So that could be changing speed and or changing direction. Yep. So, need to talk you through Newton's 3 laws of motion. Starts with the letter K. Who developed the laws of how the planets, I mean, he didn't make them do this, but who came up with laws that are associated with how the planets orbit the sun? Kepler. Yes, that was Kepler. And so Newton came up with more general laws, not just related to planets, but all motion. So 3 laws. This one is an object that's moving will stay in that same motion. Okay, so like if something's going 60 miles per hour, it'll go 60 miles per hour in the direction it's moving unless something else makes it change. Okay, some other force acts upon it. Also, if an object is at rest, it will stay at rest unless some other force acts upon it. So this is the, have you ever done, like seen the tablecloth? Or, well, tablecloth over the table, and you have salt and pepper shakers, and then somebody comes up and pulls the tablecloth.
Pulls the tablecloth out and they stay in the same place.
And everything stays in the same place. The point there is those objects that are on the table actually have a certain amount of inertia. And anyway, according to this law, they're going to stay in place unless some sort of force acts upon it. So let's see if this works. This is like my tablecloth, and this is like my salt and pepper shaker. So if I pull this out fast, okay, it just stays there. So it's going to stay there unless some sort of force acts upon it. Now, if I move slow enough, okay, it's actually the force of friction that's keeping my blibber on that page, and it will go along with the piece of paper. Okay. This is great for, I have a picture of a little space shuttle up there. This is great that if you take something and shoot it into outer space, there's no friction out there, and that thing's just going to go on and on and on unless something acts upon it, another force acts upon it. His second law says that, and to me, if you are asked on a test, what's Newton's second law, if you simply write F is equal to ma, that will work. Force applied will result in, I'm going to put m here, that's mass, and I kind of think of this as applied force, and a is acceleration. I usually put resulting acceleration. Oops. So in other words, we're going to apply a force, and it will accelerate, but it will accelerate according to kind of how massive it is. Now, whenever you see a little formula like this, what it means is we are going to multiply mass and acceleration. So force is equal to mass times acceleration. That's what it is with them, just kind of like that. So in other words, if we increase our force, what happens to our acceleration? Assuming your mass is the same. Like mathematically, if we increase force, this stays the same, what will happen to acceleration? It's going to have to go up. Yep. If we keep the same force, but we increase our mass, does this make sense? That actually then our acceleration is going to have to go down. So we have a picture of a baseball player here. So, baseball player, sorry, he's a pitcher. And so he's actually applying a force to that ball and he's releasing it. So whatever force he applies to it, that ball is going to go from basically 0 miles per hour to a particular speed. Okay. Now, as you imagine, there's all sorts of forces acting on that ball. Okay, because actually there's like the wind resistance as it flies. Okay, and then there's the force of gravity. Okay, but just in general, just look at the picture and the ball. All right. So this one, I think of like little kids, his third law. For every action, I think of little kids, if you're big brother or a little sister and you hit your little sister or big brother, they're going to hit you back. Okay? For every action, there's an equal and opposite reaction. That's Newton's third law. So what this is saying is we've got some pushing up of the, how's it go? Actually, we've got some pushing downward of the propellant here. And it is actually then making the space shuttle, in this case, go upward. So we have down and up, opposite directions, but equal magnitude. Newton's third law.
There's also other things that play a part in that too that is not on there. No, just besides the up and down.
Yeah. Yeah, it's more complicated than that.
Yeah,
yes. Yeah, definitely. But just kind of the essence of it.
Yeah.
Yeah, I agree. So that's Newton's 3 laws of motion. Now here's one for you. So forces, one force out there is the force of gravity. And Newton, again, it's not one of his 3 laws of motion, but investigated gravity. Now, the investigation of gravity is an interesting thing because we actually don't really know all of the ins and outs there is to know about gravity, but we can observe that actually as you drop something, okay, because of gravity, that thing is going to fall. If there was no gravity, it would not fall. Okay? So it's an attraction between 2 objects. In this case, it's the attraction between the mass of this pen and the mass of the Earth. Which one's bigger, the mass of the pen and the mass of the Earth? Mass of the Earth. The mass of the Earth is humongous. So if I go ahead and put a little G there. Oh, it is a G there. So this would be the mass of the pen, and this is the mass of the Earth. And this is the distance that is actually between the pen and the Earth. You might be like, well, what do you mean by that? Well, here's how that works. It's the central mass of the pen. This is the cheaper pen. The central, like the middle of the mass, so it might be here, and the middle of the mass of the Earth. Where's the middle of the mass of the Earth? Where the dinosaurs are. No, there are no dinosaurs there, but it's like the Earth's core, yeah. So that's kind of the distance. So actually, what's the difference between, well, yeah, the distance to the center. So, which would be what we call the radius of the Earth. All right. So everything has gravity between them. So we could have like this cute little green orb and this cute little gold orb, and these could be these 2 pens. Okay, so these 2 pens. So there is actually a gravitational force between them. So we plug in the force of gravity is G, and actually G, we have a lot of constants in physical science. G is just a universal constant associated with gravity. The masses, they're kind of small, okay? So right away, if we're going to take the mass of this pen times the mass of this pen, the number's going to be pretty darn small. And then the distance between them, well, it's pretty close compared to the distance between this pen and the center of the Earth. Okay? But the fact that these masses are so small, there's not much of a gravitational attraction between these 2. Okay? So force of gravity works on all objects.
So how do magnets work, but how do they overcome that gravity?
How do magnets work?
Yeah, how do they overcome that gravity to stick together instead of, like, if you drop them right next to each other, they're gonna.
Yep, and actually we have a slide on that coming up. The force of gravity, there's 4 fundamental forces. Gravity is one, and magnetism is another. And magnetism in that case actually overcomes gravity. So, yeah, that's how I would think of it anyway. Sometimes on the test, I'll throw these questions up, and so does this make sense that the larger the mass, the greater the force of gravity? By that? And then the other thing, do you see that distance actually is in the bottom? Think of it this way. at some point, let's think of a spacecraft that's getting farther from the Earth. Now, that spacecraft, as it's sitting on the launch pad, force of gravity, significant. Especially a spacecraft weighs a lot, okay? But as that spacecraft gets farther from the center of the Earth, okay, at some point, do you guys buy this, that it actually escapes the gravitation of the Earth? So the greater the distance, and so if you just kind of keep that in mind, the greater the distance, and mathematically is how it works with this, the greater the distance, the weaker the force of gravity. Okay, so the greater the distance. All right, here's one for you. So it's a really common thing, most of us, if we think of dropping, we have a bowling ball, picture a bowling ball. Okay. Then also, we use the styrofoam orbs on Friday. Picture a styrofoam orb. Okay, so they're similar dimensions, and you go up the top of a building like this, and you drop them. Most of us would say that the bowling ball is going to get there faster because gravity is going to work on that. But you wouldn't, because it doesn't. As long as they have kind of similar aerodynamics, and that's kind of what I wanted to do with that. They actually are going to, they're going to be both pulled to the Earth, but they're going to accelerate what we say, well, this says 10, but I learned it is 9.8. 9.8 is close to 10. Yeah. They're going to go 9.8 meters, oh goodness, meters per second. They're going to, every second they fall, they're going to go that fast. So the way this shows you is after 1 second, and I guess we'll have to round to 10, but after 1 second, it's going 10 or 9.8 meters per second. After 2 seconds, it's going twice that. Okay. After 3 seconds, how fast would they be going?
30 meters per second.
30 meters per second, yeah. About 30 meters per second. So it's going to go faster and faster, but they're both going to accelerate at the same speed. So I think that is pretty cool. As long as you don't have like a, now what's the difference, and actually I have a picture of this coming up on the moon where you drop two things. What if I was going to drop a feather and a hammer? Which one would hit the ground first?
Where? On the moon?
No, here.
Hammer.
Why? I think so too.
Because the feather is like, it catches air better than a hammer does.
Mm-hmm.
The hammer is much
That makes
better.
sense. Because that's true. That is totally true. That is totally true. But if we were to make, how would that work? If we were to put a bag of hammers, okay, and a bag of feathers, or in a container that take out the air resistance, they would actually hit the ground at the same time. Okay. So the reason that they go faster and faster, you guys, we start letter A. Something goes faster and faster, we say it is accelerating, exactly. Newton's second law says, if you see an acceleration like that, guess what? There must be some force driving it. In the case of this acceleration, it is actually the force of gravity. Okay, we observe acceleration, faster, faster, faster. The force is the force of gravity. And actually here in a minute, we're going to say, how much acceleration does it cause? And this is specific to the force of gravity. That acceleration is about 10 meters per second for every second it falls, or 9.8 meters per second for every second it falls. Okay, so this is my little thing I like to show here.
Hi, George.
Can we copy the
Darn it.
and penetrometer drone in the ETD?
quite yet. I haven't put the solar light in yet, but I will shortly. Oh, wow, watch this. Just a good picture there. I've got
Beautiful picture, Dave.
well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons
What's the deal? We actually, in the chemistry lab and all that, we use the term weight and mass as the same, but they aren't. Mass is kind of how much matter something has, and weight is specific to the force of gravity. Is this right? Yeah. So weight, actually, if I was going to kind of go up here, the weight that we feel, I'll use the variable W for weight, actually is the mass that we have in our body or whatever object you're trying to weigh times the acceleration due to gravity. And we use the symbol G for the acceleration due to gravity. And as I put over there, that G actually has a specific value. Like this textbook goes with 10 meters per second You'll oftentimes see me go with, like I said, 9.8 meters per second. Okay, so that is weight. So in order to really know what the weight of something is, you have to take the mass of that thing times 9.8 meters per second. So here's the deal. If you step on a scale, okay, you are stepping on a scale and it is taking your mass and basically taking into consideration the acceleration your mass has towards the center of our Earth. What do you think if you were on the moon? If you're on the moon, you do have gravity going on. It's that big constant G, which is the same for the moon or the Earth. So I'll put M1, M2 divided by D squared. If you're on the moon, what do you think about the mass of the moon compared to the mass of the Earth?
It's smaller.
It's much smaller. So if you're on the moon, the force of gravity is much smaller. If you're on the moon, this actually G term changes, and if you're on the moon, your W is less. That's totally it. So mass is the amount of matter in an object, and weight is, and we're going to use the variable W. There's too many things in physics anyway that has the symbol W, but weight is the mass of the object times the gravitational pull it's filling. That G is going to be, the G on Earth is 10 or 9.8. The G on the moon is smaller. Okay, so the mass of an object will be constant, but the weight will be determined by the thing it's standing on. So I mentioned that on the moon it's less. How much less? It's much less. So if you weigh 100, would this be right? Well, if you weigh like 60 pounds, anything that weighs 60 pounds, this works. 60 pounds on Earth will weigh 10 pounds on the moon. Okay, so it's 1/6 on the moon. Yeah, on the moon. All right. A few more terms, sciencey terms, very sciencey terms, everyday things that we run into. Momentum. So momentum, like you can read up here, momentum can be calculated if you know the mass of an object and how fast it's going. Here we go. This will be my Mack truck, and this will be my bicycle. Which one has more mass?
The truck.
The truck. They're both going down the road at 30 miles per hour. Okay? And momentum is their mass times how fast they're going, but they're both going 30 miles per hour. Which one has more momentum?
The truck.
The truck, exactly. The truck has more momentum.
It's going to take more to stop it.
It's going to take more to stop it, yeah, exactly. So that's momentum. All right. Well, actually, let's change this up a bit. Now I have two bikes. They're both going, one's going 30 miles per hour and one's going 60 miles per hour. Okay, so which one has more momentum? The one that's going 60, yeah. Exactly. So if you want to change the momentum of something, you need to apply a force. Seems reasonable. And then this is just kind of tidbits, kind of cleaning up. I mentioned this with kind of the baseball, the picture throwing a baseball. Oftentimes there can be all sorts of different forces working on the same object. Like in the case of the baseball, it was the pitcher's thrust, and it was the force of friction in the air, and it was the force of gravity. So, and they all combine to make what we call a net force, kind of like your net income. Okay, I think we already talked about this one. The fact that objects fall faster and faster, about 10 meters per second for every second they fall, they keep going faster and faster. That means because you observe acceleration, there must be some sort of force working on them. Okay, so again, a little bit about momentum. And this actually, if that's my sun, we've been kind of pretending that's my sun. I could be a planet orbiting, okay, the sun. Things that orbit and or things that rotate have an extra type of special momentum called angular momentum. The thing with the cars, that's kind of like what linear momentum. Cars and okay, so angular momentum. So to calculate the angular momentum, we take the mass of the object that's spinning or rotating times the velocity. Now velocity has both speed and direction, times the radius about which that object is spinning or rotating. So we have three things multiplied by each other. So we've been kind of talking about this a little bit. If I increase the mass of the object that's spinning or orbiting, does this make sense? I will increase the angular momentum. Okay. What happens if I increase the radius?
Slow it down.
If I increase the radius with the same angular momentum, I'm running out of things here. If I increase the radius, the same angular momentum, what he's saying is my velocity has to get less to keep this the same. Assuming I get this, that's the same. I have a very good example coming up of somebody who's spinning on ice skates. So I have a law coming up here. I'll underline conservation. Everything's conserved in a natural world, okay? Matter is conserved, atoms are conserved, energy is conserved. When I think of conservation, I think of it saved, and that's what I mean, it's saved. You can track that quantity. You can track momentum, energy, matter. So as planets orbit the sun, which is a type of angular momentum would be involved, the angular momentum needs to be conserved. Yeah, and so this goes back to what was said recently then. If angular momentum stays the same, then as the R, I have a up arrow, as your R increases, your radius increases, your velocity must decrease. So here's the deal. We talked about the planets. What's the closest planet?
Mercury.
Mercury. And then Venus, and then Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Oh, that's right. We ran out of Pluto. Yep. So the point here is, if I'm out here like with Neptune, my R value is pretty high. And what did we say about Neptune as far as how fast it goes in its orbit compared to the Earth?
It goes way slower.
It goes way slower. Yeah, exactly. But this says actually related to a single orbit about the Earth. So let's pick on the Earth, or a single orbit about the Sun. Let's pick on the Earth orbiting the Sun. Starts with letter A. What did we say when the Earth is closest to the Sun? We call that? Oh, it starts with letter P. Sorry, I'm sorry. Starts with letter P when it's closest to the Sun. I think of like en garde, like Perihelion. I saw Courtney mouth. Perihelion. Yeah, this is perihelion. Starts with the letter A. So what do we call it when it's farthest from the sun?
Antihelion.
Almost. Aphelion. I'm not sure where that comes from, but it's farthest. So
There's
we
an
have
app for that.
aphelion. Right? And so here, if we apply the conservation of momentum, and this kind of gets confused with a little bit his third law and second law, but this we said that is the Earth going to move fastest or slowest out here at aphelion? Slowest, yes, exactly. And that's consistent with this too. So as we increase the radius, we had to decrease the velocity to keep the same momentum. So conservation of lots of different things. Our universe counts on it. So like conservation of momentum, whether that's angular or just straight linear momentum, conservation of matter, conservation of energy, conservation. Okay. So in science, a lot of times we get clues to what's going on by tracking these quantities, knowing that they have to be the same. So here we have the ice skater. When she has her arms out, she has a large R. Okay, so that means her velocity, a large R, her velocity needs to be lower. Okay, when she brings her arms in, her R decreases and her velocity must increase. So that's kind of how that works. And this is what we just described. Antihelion, sorry. This is the aphelion, okay? So aphelion, and like you said, we go slower out here. And this is perihelion. Let me go faster here. And that's actually Kepler's second law. All right. So here's one for you. This kind of blows my mind, I think. I'm going to change it up. That's not going to be the sun. I'm going to make that the Earth. So I have a slide coming up here to kind of show you that our Earth has all sorts of things in orbit about it. Now, as something orbits the Earth, well, forget that. Don't think about it orbiting. As something's near the Earth, like, in outer space, we know it's inserted in orbit, just sitting here. Does this make sense that actually it feels a gravitational pull? Okay, and it does. And I'm going to kind of show you that it feels a gravitational pull, and it does go that way, but it just kind of goes forward because that's how it kind of got inserted in orbit, forward a little bit, so it misses falling to the Earth. So it's going to fall to the Earth, but it's going to go forward a little bit, and it's going to miss the Earth. It's going to fall to the Earth, but it's going to forward a little bit, it's going to miss the Earth. Okay? So it's actually something that's in orbit is actually kind of a free fall towards the Earth, but because it has a little bit of direction in this way, it keeps missing the Earth. Okay? So I think that's kind of cool.
What causes falling stars?
Causes falling stars? So if that's the Earth, the thing with falling stars is the Earth kind of plows into some kind of material, falls through the Earth's atmosphere and burns up. So this is the Earth's atmosphere, so something just kind of falls in, gravity, and it makes a streak as it falls in. Yeah. So the falling stars, if you were on Earth before the streak happens, and you were kind of looking at all the beautiful stars, there would be no star that actually fell. I mean, there's nothing from where it fell, and you'll just see the streak. Yeah, that's falling stars. Yep.
Is it the same thing with space junk? When it comes down, it just enters the Earth's?
Yes, yeah, and that's a concern, Actually, I heard today they were talking about why Space Wars and why like people don't do more, like if you have an enemy satellite out there, we'll just kill it. Because the thing about that is it breaks into all these little pieces and it can actually do harm to your other stuff. Not to mention, it can put something on a trajectory to fall to Earth. So, yeah. Yeah, there's been a few like biggies that they know when it's in a decay orbit, and they can try to escort it down or try to help it fall safely. But yeah, it burns up. So this actually is kind of a weird diagram. We're showing the person climbing a very tall tower, and this person climbing a tower, oh, now I see now. We have 3 scenarios. These 2 people right here, they don't have what this person has. These 2 people don't have like the jetpack, exactly, thank you. So they climb this tower and sillily, they just like walk, they're like lemmings, they walk off. This person climbed a tower and instead of just walking off, he just took a running start, okay? So she took a running start, so he actually finally, he went a little bit farther, but he definitely fell to the earth. But can you see where he went farther on the earth?
Yes.
So this person has a jetpack, okay? And he's actually going to fly off, and the earth's going to pull him towards the earth, okay? But he is actually going to miss the earth. So he's going this way, he's being pulled towards the earth, but he doesn't fall to the earth. It's kind of like I was trying to describe a minute ago.
So he's going fast enough to counteract the pull toward the earth.
Yeah, he's going fast enough to, to stay, and he's staying in orbit. Yeah, he's going fast enough to miss the earth as he falls. So he's still falling. This dude's still falling, but he's going fast enough to miss the earth as he falls, because it kind of curves.
Have you seen that one thing they have you can pay, and it's like a plane, and they go up really high, and they take it straight down, and you can experience like free fall?
Oh, I've seen that, yeah. And I think Stephen Hawking was on one of those where he just, you're free falling, yeah.
Mm-hmm.
And so when we watch videos of people in the International Space Station, they actually, it's not true to say that there's no gravity. They don't feel any gravity, but because the ISS,
they're indefinitely falling.
Yeah, they're just always falling. That's cool. So they feel weightless, but there definitely is a weight involved. So here they are. Let's take a look at this video right quick. Speaking of, so these are the happy people. I just loved. So this is kind of showing you the same thing where somebody is firing a bullet out of a gun, and in A, just a certain amount of velocity, in B, even more forward velocity, and in C, enough velocity to go ahead and insert itself in orbit. There's actually a D that's not shown here, where it has enough velocity to escape the gravitational influence of the Earth. This was a figure drawn a long time ago, back in 1731, where the scientists actually drew a very similar thing with regard to having something. Well, that's a good place to stop for today. So when we meet again on Friday, remember we're over in the Chem Lab. Bring your notes, and if you're doing notes. Otherwise, just bring something to write on. And we are still going to go ahead and make a comment. So we'll kind of talk about that sort of stuff in the Chem Lab. All right. So nothing due for Friday because we didn't get through a whole part.